Well, welcome to today's lecture. We're going over finite element analysis. Yay! Or we're not. What?
No, we're doing it.
Yay! Okay, sick. Okay, so for a kind of outline, we have a 2-day lecture series on FEA. Today is going to be more of an overview of FEA and kind of brief examples. This content is like way too big to even like fully do it justice, but we're going to attempt to do something resembling that. The first day is going to be kind of overview. How does the FEA method work? Because a lot of people just like don't see what's behind, like what is it actually solving. When should I use FEA, and kind of like give a brief example of how FEA connects to failure theories. And we're going to borrow an exercise from Chris Lee's FEA class. If you have never like set up or done a study before, you want to kind of go a little deeper into like what can I actually do with FEA. As always, we're going to grab Daniela's like, so why does this matter? FEA allows you to go from hand calcs to like much more complex geometries. And like numerical solves all your problems, but it again is a tool. It's not a magic thing that like instantly gives you the right answer. It allows you to optimize and analyze systems that just are not possible to do with hand calcs. Like we just don't have the analytical tools to do that. Also, fun fact, Daniela did a master's on nonlinear FBA on chicken embryos, which is really sick. And I don't know that much about it, but you should go talk to her about it. But she mentioned that, and I thought that was really cool. As always, we have videos to share for y'all. The second image, the efficient engineer video, we steal a lot of screenshots from that. We are inspired by it. We don't steal. And we just are going to give kind of like a verbal like explanation of what's going on, but these videos are highly like visual and really helpful if you want to look at that. And I hit it twice and it should go to the next thing. No, there we go, cool. As I said, this class, like, there's just way too much to cover in a 2-day lecture. And you like to get a good understanding of FEA and like get a like sense for it. Like it just takes time and experience. Chris Lee told me, I'm pretty certain, like put some air quotes on this, but the window for getting a master's through FEA is like slowly closing, but still feasible. As in like, there's just so much FEA out there that like, you can probably add something new to it, but like it's there. I'm like 90%, he told me this once, like during FEA, 2 years ago. But at some point you kind of just need to pick a book and then read it. I am a very big fan of like the ANSYS like help or the theory guide. So if all of us have access to ANSYS, if you download it if you go to the IT wiki page, and then once you have it downloaded, all ANSYS products, if you like go to your search bar and you just type in like ANSYS help, practical understanding of like what's behind in the theory, and then the rest of it is literally just screenshots of the program. Because a lot of these FEA programs, they just give you like way too many options and it's very overwhelming. You have a question, Daniel, or you?
Yeah, don't download ANSYS 21. It won't work.
Oh, really?
We use 18.
Do we have ANSYS 21?
ANSYS 19.
Oh, that's awesome. Thank you for noting that. ANSYS also has Learning Hub. Or sorry, were you going to say something?
We have something past 18.
Okay, cool. Yeah, okay. So what is FEA? FEA are rainbows. Well then, what are rainbows? Rainbows are visions, but only illusions. And come and join us, we'll show you the rainbow connection. But like in all seriousness, like the reason I do this is that like the FEA or the rainbows, they give you nice, pretty colorful plots, but who the fuck knows if it's actually correct? So like the main takeaway to have from this lecture is that you need such a heavy like helping of skepticism when you like when you're taking FEA and you don't want that to be your only source of like, I'm confident this part will not fail because the FEA told me so. Like there are so many aspects of this, from like rounding off errors to discretization errors to like just plain old human error. When doing your model, you need such a healthy handful of kind of skepticism for it. On the vast, just super outline of FEA, what you're going to do is you import your model, you assign loads to it. You then need to create boundary conditions and supports. And a lot of the times from that, you have to simplify or make assumptions about the loading conditions. And so like if you have a symmetry plane, you should like bisect your model in half. So now you only have to model half of the part. If you have like a fixed support, are you comfortable saying, okay, like I have this pin joint right, or I'm bolting it to the wall and I'm just going to say this is an infinitely stiff wall and I don't need to care about how much like what spring force or how this is that something that can actually work. You then mesh it, you run your study, the study hopefully converges, and then you analyze the results and see if it's within a reasonable doubt or if it's something that's useful to you or just kind of chicken shit. Like why we need FEA and the FEM. FEM is the finite element method, if you haven't heard that before. Why do we need these approaches? Or like why do we use them rather? For many engineering problems, we can make really useful 1D or 2D abstractions, and it gives us enough useful information that we can do something with it. So like we can abstract the like 3D stress straight to a 2D model. We can do like 2D Euler Bernoulli bending models. We can do this torsion model. And like all of these are close enough to reality that we say we can do something with it. All models are wrong, but some are useful. This is not always the case. So like, for example, if we are doing like a 2D cantilever beam, we've done this in class before, we can say, okay, well, we know the entire thing is in static equilibrium, and we can say at any section across this beam, like I can solve for my shear force and my moment acting across this like imaginary slice of face. However, in the real world, we're not always working with just simple beams for the matter. And we might have like a 2D bracket or something like this. Some genius out there might have derived some analytical way to do this just with hand calcs, but our simple assumption of like just cut through here, we can't really say, okay, well, both of these faces are in like equilibrium for the entire static, and we're just going to say the shear force and moment across these two faces are like divided in half of what it was be of this. Like that just doesn't work out that way. We can't say the entire body is in equilibrium. However, by discretizing our geometry and breaking it up into a ton of like thousands of tiny little like elements or sections, we don't have to say the entire body is in equilibrium. We just have to say each one of those elements is in equilibrium, and then apply that and do some useful work with it. So that's called discretizing the geometry. When you discretize the geometry, each one of your sections, depending on how you're choosing to model it, is then called an element. Elements intersect with each other at nodes. This is a pretty clear distinction. It honestly didn't hit home for me for a while. Like, what's the difference between element and nodes? Element is like if we're looking at these two triangles or these triangles over here, like the element would be the entire triangle. What the individual nodes are would be the individual points where the elements intersect with each other. This is really critical information to get in your head and like have clear definitions on. This is pretty important to keep in mind because what allows the FEA process to work is that there will be continuity from element to element at the node. Meaning that if I have just right here, I have a simple line element. At node 2, the displacement for element 1 will equal the displacement for element 2. That's critical because that allows us to assume continuity, and that allows us to then, and more details on this later, that lets us build the global stiffness matrix, and like is kind of the core process of why this like model and assumptions can work. What the hell? Okay, 1 second. I think my slides are out of order. Uh-oh. Sorry, 1 second. Where did you come from, bud? Okay. Sorry about that. Sick. Another additional thing about nodes and why they're critical is that your boundary conditions and the loads, whether they be a thermal load, mass flow rates, like static load, they can only be applied at the nodes. Not like for the longest time, I thought like, oh, you're applying this to like the face of the element. That's not true. You're only applying it at the node. And that like what the solver does is that it solves it for each individual node, and then it takes the entire displacement or whatever you're solving for, your critical value, for all the nodes of the element, and makes a generalized field for each element. But it's based upon the nodes. That'll be clearer in just a minute. For meshes and the different types, for elements and the different types, there's a wide variety of element types that exist out there. And we'll talk more about this next week about when we get into like the different types of modeling and the different types of studies you can run. Like in the simplest section, you can't just have a single node that you can't really represent any space with that. You have a line element, which is simply just two nodes. Within those two nodes, you can like have different types of applications and different types of ways that it'll stop. So like for a 2D line element, you could have a truss where it's simply just a two-force member. It doesn't support any moments and only supports axial load in the direction of the element. For a beam, you could have like it supports axial load and as well as like stiffness in the like perpendicular direction as well moments. And for like a frame, you now have like, okay, it's going to support moments and also in the other two directions of rotation, as well as all stiffness. We'll get back to this when we talk about like how many degrees of freedom an element has. But what's important to like remember for right now is that you can have like a line element, you could have a surface element, which just like represents 2D space. And there's several ways you could do that with like quads or triangles. This is a kind of a sneak peek ahead, but like this element right here and this element right here we call first degree elements. And this element right here and this element right here we call second degree elements. Second degree elements have an advantage over first degree elements in that they have a node at this intersection or at the midpoint between like the corners of the element. More on that next week. And then lastly, you can have like a full solid 3D element. Very commonly, you'll see a 4-node tetrahedron, or often called just a tet. You'll also very commonly see bricks and sometimes pentagonal, like bricks, like cubes, and sometimes you'll see like a pure. That's what I'm looking for. Prism. There you go. Thank you. All three of these have distinct advantages over one another in different applications. Again, we'll talk about that more next week. All of the elements collectively come together to form the mesh. Meshes can get funky. Meshes can get weird. There's a lot of like when later today we'll be doing a SolidWorks tutorial or SolidWorks kind of example, and SolidWorks doesn't give you a ton of options with the mesh. There's some things you can do. When you get to more serious programs like ANSYS or COMSOL, you get a ton of options on how you can manually change the mesh or add like inflation areas or different transitions, or like you can describe this area, I want this type of mesh element, but then I want you to transition and use quads over here. There is so much to do with meshing that like often I think one of the most important things of whether your study will be useful or not is that did you adequately spend enough time to make sure your mesh is realistic or will give you results that will match reality. Because of that, like intuitively determining the quality of your mesh is something that kind of just takes time and a lot of exposure. You get like exposed to experts, mentors. You need to read a lot. There's a ton of like, there's some actual statistical quality to it, and then there's a lot of like hidden rules that like are written down somewhere, but like you kind of just don't know until someone tells you about it. However, there are a lot of like few low-hanging fruits that are useful to us and that we can discuss and that like could be used as a rule of thumb, but isn't true in all cases. So the first thing we're going to do is we're kind of going to do a class exercise. It's just a group discussion. There are no right or wrong answers. On the left side, we have this, like, we're going to assume we have a 2D just kind of plane bracket right here of uniform thickness, and it's very thin. So we're going to approximate this as plane stress. And on the right side right here, we now have a mesh of that a condition, and we are using a 2D surface mesh triangles here instead of quads. And on the left side, we just have a fixed support right here, as well as on the very corner right here, we have our load applied in the top right. Just as a group discussion, like, how do y'all feel about this mesh? Is there anything that like stands out to you in particular, or things that you feel like maybe it's worth discussing?
Worried about mesh size around the fillet on the bottom right.
Yeah, that's a great place to start. So if I pop up right in there, I ultra instinct, okay? But Daniel's exactly correct. If we pull that right there and we blow it up a little bit, you'll notice like this fillet right here has just really jagged curved edges that are unlikely to give us a realistic approximation of what's going to happen at that fillet once we deform it. So like, what the fuck is that? Compare that to the first course at the hole that was inside the piece. This is like better. It's probably, I would probably prefer to have more there, but compared to this seems like a decently reasonable like mesh for that corner right there. In addition to that, there's just not a ton of points that represent that there's not a ton of points that represents that curvature. 2D stress triangle elements in this case also have a disadvantage that even after deformation, before and after deformation, the connection between nodes is always going to be straight. Meaning that if you have a really like rough, jagged edge corner right here, and you now are like deforming that, I would be very, very doubtful about like the values of stress that it says is going to happen at these areas, because like it's maybe deforming way too much or way too little, because these connections can only move straight and it doesn't have a good representation of the curvature. There's a second point later that 2D mesh elements also have a disadvantage of that I'll talk about in just a second. But before I do that, if I go back here, is there anything else that feels like is maybe worth discussing? Totally no right or wrong answers. Just throw something out. Yeah, perfect. So if I pull this out over here, if we look over here, remember, as we mentioned, the distributed load, loads and supports can only be provided at the nodes. So for that distributed load I had beforehand, I can really only distribute it across these three nodes. And notice for my fixed support here, I can only fix it at the nodes that are connecting at the wall. And so that just kind of brings home this point, is that we had a distributed load that now we're only doing it for 3 points. We don't know the actual loading conditions of this piece. Like we're not given how much force is acting upon it, like what the stiffness of all this is. We don't really know. This right here, this distributed load only being applied by nodes, is actually not that egregious depending on what your condition is, but it's still it's still worth it to point that out and say that, like, well, okay, maybe I had a much longer distributed load and I don't have that many elements, and I'm not certain that's a great approximation. But it's good. It's a good thing you noticed that. The bigger thing I'd be worried about right here is that this is at the end of the plate, like sort of like a cantilever, where we're going to be expecting the most deflection. Where we're expecting the most deflection, we have like really large elements right here. And the elements, the deflection is again only calculated for the nodes. And so because we have such large elements and we're using 2D strain, we're using one first order 2D surface elements, like we're only going to get like a rough approximation of the average strain at the center of each element, rather than like if we had like bumped this mesh up and made it much tighter, we would have still again only average stress at each element. We have so many more elements now that I could feel a little bit more confident that I'm doing something that is a little closer to reality. So there's a few ways that we could definitely improve this mesh. Number one, more elements will definitely improve this at the expense of more computational time. That's not always like fully true. That doesn't mean for every mesh you should just send a slider to hell and be like, I'm just gonna put a tiny mesh on this, and then I'm okay waiting the 4 hours because I need to go to McDonald's anyways. Like that's a approach, maybe not the best approach. Additionally, changing the element size you're doing will also help this. So changing to a second order quad element would help on this. Again, second order elements have a node at the middle of the connections. And quad elements are a little better suited for this specific plane stress case because there are more nodes and it's a bit easier to represent. The advantage of that though is that quad elements, like it's a little difficult to estimate curvature with quad elements. So that's why it's you're more commonly going to see like triangular elements on curves, especially for like 3D geometry. But in general, quad elements give a better approximation of what you're going to see in reality. But it's not always the most accurate for like weird geometry. This excerpt, I'm not expecting y'all to read it at all, but this exercise is kind of taken straight from chapter 19 of Shigley's. Highly recommend. If you want to read through like each specific case and why these elements is maybe not the best way to go about it. Yeah. Okay. That took way less time than I was expecting it to, actually. So I was hoping to get closer to like 9:15 or something like that and do a temp check. But what's up?
I have a couple questions.
Yeah.
One is, are these meshes, can we think of them as going through your part? Like is the whole part?
That's sorry, keep going. That's a great question. So if for this specific case, no, actually. Because when you do, so this goes back to all the way over here. There are different mesh types. For the line truss, that's just a kind of like 2D case where you just have like length and translation there. This is a surface mesh, meaning that I can approximate this flat plate as a surface, and in my solver, I can assign a thickness to this actually that it's using for calculations. But the advantage of that is I don't actually have to make a 3D mesh and sacrifice way more computational time. So like we'll talk about this next week. There's like concepts of like beam and shell elements versus solid elements. Like beam and shell elements are kind of analogous to, okay, I have like a line element and a surface element. And the advantages of those is that you're like getting comparable results at a fraction of the computational time than if you just have if you have like a really tiny like solid element inside your mesh. So like for going back to these guys right here, these are all solid elements because we're doing like, it's for all of these geometries right here, it'd be a really big stretch to say for this thickness right here, I'm going to say that's mostly plane stress. And then like, it's really difficult. It's also, I think, impossible as far as I'm aware to go from like, okay, I'm going to model this section right here as solid geometry, and then I'm going to transition to like 2D geometry right here.
So you can make like section. I don't think I've ever seen a section view of like an FEA, a solid FEA.
Yeah. That's some actually you can later. Julia, did you have a question?
For second order, you said a change to the second order file. Is that any slide change?
Yes. So for this guy, right, I didn't, there's not a visual representation of it. But like just this slide right here, like these are two options that you have. And like this slide right here is just like a bullet point list of like what this paragraph says right here, if you want to read through this paragraph. But like, and like I said, this is just ripped straight from Shigley's. This entire exercise. I had one more thing I was going to say. Any other questions? Yeah.
Yeah, my other question, I guess, is, so I can see how maybe you could change it from quad to and have just triangles around the circle, and then maybe mess around and get it, exactly how you want it. But at some point, wouldn't it be easier to just double the number of nodes or something?
Yeah.
And how do you kind of balance that when you, does it like tell you an approximation of how long it's going to take to solve?
Typically not. As far as I'm aware, like so for reference, my FEA experience is mostly from SolidWorks and ANSYS. And there might be some elements out there that says like predict like expected solving time. In general, this looks like a static 2D case. I would be shocked if this took more than 30 seconds to run. And like especially when you get like, so for a simple case like this, it's not that you're not sacrificing that much, just saying like, fuck it, I don't want to think about this, and you just go like, I have a mesh size of like 0.1 millimeters, and you just have like a 20,000 element size thing. It probably won't take that much long to solve, especially if you have a pretty simple loading case and relatively simple geometry. When you get into, so like pretty like the next section we're going to talk about is that now we've meshed the object. How do we go about in solving that, and like what do the like governing equations for that look like? You'll see, so for something like this looks like a really tiny mesh. Like I don't even want to begin to think of how many thousand degrees of freedom exist for this model. So you'll get a quick insight to like as a snippet ahead for like 5 minutes. Each one of those elements that I mentioned before. So like if we start with this beam bending, I'm saying this is going to be a truss shape, meaning that for each displacement, each node, I only have like 1 degree of freedom where I can only move like axially in the direction of the load. For each other subsequent event, so for a beam element, I could then say like, okay, well now I can move axially, I can move up and down, I can translate. Now I'm going to say I can also rotate in this specific like direction. And then for a frame element, I'm now going to have, so for here, I had like 1 degree of freedom per node. Here I have 3. Yeah, 3. And then here for a frame element, I'm now going to say I have 6 degrees of freedom, where each one of these elements can translate X, Y, and Z, and also rotate like yaw, pitch, and roll for each element. Each one of those degrees of freedom for each element, that you need to solve a linear system of equations that describes how that corresponds to your load case and your load case and your boundary conditions. So is that like helpful for kind of like starting to understand?
Yeah, so it's like exponential with the number of nodes.
Kind of like, yeah. So I don't know what the actual like relationship is, but like it definitely is like the more nodes you start to add, the more computational power and time you're going to need. And like, so there's a lot of reasons. So for like, when you're doing like massive CFD simulations, so like for F1, for example, F1 like actually limits the number of computational hours you're allowed to use on your team, just because like if everyone had the opportunity to just like throw millions of dollars into AWS and like just load things, like it just would take forever and you would be optimizing for the randomest things. So you need to like in a competition sense, like that seems to be fair to where you need to limit and like prevent that. But also in the real world, like these like simulations can take like days to run if you're doing it, which costs money. Exactly. So for reference, and I'll talk more about this next week, not this summer, but the past summer, I was doing a ton of CFD runs And like realistically, I could only get 2 or maybe 3 runs a day done. And if all of a sudden one of those runs crashed or didn't converge, I've now wasted like 4 hours that, I mean, I'm getting paid for. The company doesn't probably like that, but yeah. Any more questions before we get into the rest? Schwanky. I'm gonna sip my coffee. Okay. So I talked about the overall FEA results, like how you go from like model, loads, boundary conditions to result. We've now arrived at our mesh. How do we go from mesh to results? That is a very complex analytic, like numeric process. But here are some like rough overviews on how this works. Full disclosure, we've taken like screenshots from Efficient Engineer and like are going to just kind of verbally explain that. I highly recommend you watch both the videos at the start of this lecture, just because you like it gives you the most like graphic and visual way to like understand what's happening that I think I've ever seen. But in rough like outline steps is that, and for each one of these points, I'll explain what it's doing. You're going to calculate the stiffness matrix for each element according to like the element's geometry and its material properties. What is the stiffness matrix? Just a second, I'll get to it. From the stiffness matrix, you take all of those together and form a global stiffness matrix that describes the entire piece. From that global stiffness matrix, you calculate your force vector depending on the loading conditions and the boundary supports of like what reactions am I expecting at this like fixed wall and what forces are acting on like this an individual element or individual node. And then from there, these last 3 or 4, I believe, are all kind of just within the solve and what actual like PDEs and like matrix operations is doing to solve. You're going to calculate each individual nodal displacement. From each individual nodal displacement for your entire element, you're going to calculate a displacement field for the entire element. From there, you like from displacement, you can calculate strain, and from strain, you can calculate stress. That was a lot of talking and no visuals. We're going to have a bullet point for each one of these and how this works. But like as the overall process, this is how it works. Step 1 is calculating the stiffness matrix. So to start with the stiffness matrix, for each node, I'm going to have like a U vector. And the U vector is going to be all of the degrees of freedom in which I can move about a specific nodal point. So for this 2D stress element right here, where I have a beam, for each one of these nodes, I'm going to call this U1 and U2. I have this matrix right here where I am able in a 2D space to go axially and perpendicular, so I can move any there. So I have U1 and is that a U or a V? That's a V. Okay. I have a U1 and I have a V1. For each one of those, I can also rotate like I can rotate about my pin joint right there, or I can treat it as a pin joint, and I can rotate in this plane. I cannot rotate out of plane, so I can only like go this way. I can't pitch in, pitch out, or yaw. So for this individual element, I have 6 degrees of freedom. For more complex geometry, your number of degrees of freedom also start to go up. An advantage of solid something with solid geometry is that you don't actually calculate rotation for each one of them. You have just 3 degrees of freedom of translation, and rotation is accounted for in just how it's moving in XYZ space. So this is like for that first element where I was talking about it's not rotating in and out. However, if I now say, okay, all of a sudden this is now a frame member that's operating in 3D space, I've now added 2 more degrees of rotation about which I can go. And remember, this is still like a approximation and abstraction of like 3D space. But now all of a sudden I have this many degrees of freedom for just one element. From this many degrees of freedom, I'm going to make an assumption about how each of my material, each element is going to deform that is like kind of roughly based on Hooke's law. So remember for Hooke's law, high school physics, you have a spring, and the spring force is equivalent to your spring constant and how much displacement it's moving. And so in a 1D case like this, you just have an unstretched string. As I add more mass to it, my displacement increases and my force of the spring linearly increases according to a rate of my spring constant. FEA does a very similar thing where I say the forces acting upon each node are going to be equivalent to whatever my nodal displacements are that I calculated, so my degrees of freedom, and some stiffness matrix. What does that stiffness matrix actually look like? For each one of those individual degrees of freedom, I now have a approximate stiffness constant depending on material properties and geometry. For each one of these directions. So again, within just those this simple 2D element right here, I then now have this massive matrix that I would have to solve, and it's just impossible. For this simple case, it's actually not that bad to solve. You could solve it by hand, but this is just one element within my geometry. What the actual stiffness matrix looks like in real life is going to be dependent on material properties. So we aren't going to spend time each time discussing we're not going to spend time at all discussing every single one of these, but for example, force in the axial direction is just your stiffness of how much it's resisting and moving is depending on the cross-sectional area times Young's modulus divided by the length of your element. There are equations that link each one of these motions to each one of these displacements to whatever degrees of freedom you're acting upon right there. So FEA just handles that for you, but we include this because we want you to understand this is what's actually happening when it's solving it. It's not just going oh, I know the equations for that. These equations come from the geometry and the material properties for whatever material we're working with. And again, all of these equations and what we're going to do in this class are relying on linear isotropic materials. When you get outside of that range, you're getting into crazy complex mat sci and tensor math that honestly you could get a PhD in, and Chris Lee understands, and I hope to one day understand it like Chris Lee does. Okay. So basically, as a very, very rough approximation of what that entire process was, and we're representing it more visual rather than matrix form, we're treating each element as if it's a tiny spring. And we are now, depending on how many degrees of freedom we're caring about, we have different spring constants in different directions that correspond to the materials, to the elements, geometry, and material. So for this step shaft right here, we could represent this and kind of do a real quick written example of we said, okay, we're going to treat each one of these elements right here, or each section of this step shaft as if it was its own element. And for the stiffness matrix for this entire model, we're going to say this first section has some spring force equivalent to K1, and this second section right here has a larger spring force equivalent to K2, just because it has a larger geometry and will be stiffer. Does that rough idea work with everyone of you can approximate your nodal displacements and relate it to the forces on some stiffness matrix? Yeah? Okay. When you guys get into ESA, if you haven't taken ESA or if you recall back to ESA, we make the same assumptions when we're calculating the natural frequency of an object. We are approximating it as some first order spring. So that is the stiffness matrix for each element. For every single one of those elements has this massive matrix now. In order to solve everything, I need to make a global stiffness matrix for my entire geometry. So what does that look like? So this is from Efficient Engineer. Say I now have just a cantilever beam right here, and I have element 1, 2, and 3, pink, yellow, purple. I almost forgot the color names for a second, I'm not gonna lie. To make my global stiffness matrix, rather than all of those like equations that I showed before, we're going to represent it as these like individual pink and like squares. So you can imagine each one of those squares that are a different color representing your like row and element, your row and column. To make a global stiffness matrix, I have to go to and relate, okay, the displacement at node 2 at the end of element 1 is going to be equivalent to the beginning of element 2. So this goes back to that key thing about nodes, where you have to say nodes are what connect elements, and that continuity is what is the critical kind of like link that allows us to make the global stiffness matrix that solves it for everything. So in like other terms, like this goes back, oh, sorry. I guess I thought I had a representation of it. That goes back to that thing where like in this section right here, I'm now saying the end of my elements are equivalent and they must be equal to whatever my second element is here. That help? Okay. How's everyone doing? Sick. We're almost there. We'll get to do fun stuff like hands-on. Second part, or third part, I want to calculate my force vector depending on the loading conditions. So going back to like F equals KU, I now have my global stiffness matrix. Say I want to reorder it, or not reorder it, but now I no longer have a cantilever beam. I have some like geometry that is dependent on, like I have some simple truss structure. This on the right is still for that cantilever beam. This second image, this is what this looks like for when I now have, okay, now all my elements are connected to one of each other, and I need to represent it in that way. There's a critical piece that you also need to keep in mind, where all of a sudden I no longer have connections that just go in a linear fashion, like node 1 connects to node 3 and 2. So I have intersections like both here and here. For each one of those like connections, I now need to apply a rotation depending on the geometry and how it connects to the global coordinate frame. So in the past, close your eyes. In the past, all of my elements were aligned with just, and I guess I should have included it here, but like just imagine I have an XY axis here. For when I have this connection right here, only my, if I still have a global reference frame of like XY, only my pink element is aligned with that global reference frame. And so going back to just like early days QEA, what you would do to like make this compliant with the global reference frame is that you would just take a rotation matrix and apply it to the elements that correspond to this. So that's what the FEA is doing as well. Just a minor thing to bring up that is also existing. The last like visual thing to understand is I previously had a pin joint right here and a roller joint right here and an applied load at this top right corner. I can represent those boundary conditions as just forces and fixed displacements on my entire global system. So for right here, this is my force vector, this is my stiffness matrix, and this is my displacement vector. For my first element, like I had a pin joint right here, I'm going to have corresponding forces F1 and F2 in the XY direction in my force vector. And for my displacement right here, I'm saying this is a fixed, or this is a pin joint. It cannot move in the XY direction. So that sets up my like system of equations for those two. Similarly, point 3 right here is a roller joint. And so in the Y direction, I'll have some reaction force F3. And in my Y direction for my displacement, I'll have 0 because it cannot move in that direction. And lastly, F4 is just the reaction force that's being pushed on it. So again, this basic idea comes from you just set up a system of equations F, K, and U. And the last final discussion is how do you actually calculate those like displacements. We'll talk more about that next week, but like the basic understanding and what I think is kind of cool is that in engineering, what we've done in this class so far, we've gone from I want to solve for like I'm going to use my loading and geometry to solve for my stress. And then for my stress, I can look at my stress strain curve and use Poisson's ratio and Young's modulus and go to my like displacement and everything here. FEA solves displacement first, actually, and then using your strain for your change in length divided by your original length for like each nodal element, it calculates your strain, and then from strain you can get to stress depending on your Young's modulus for your material. I think that's a really cool thing that like I never really fully understood, but basically like because we're doing F equals Kx or F equals Ku, we're solving for displacement first, and then on the backtrack can solve for stress. That's the basic like rough understanding of how the FEM method works. It is a tool. It is a it is a numeric method for solving these governing equations. These equations are the PDEs that model mechanical behavior. They are not true. They are not like the one and all. It is an approximation of your model. And like all approximations, some are okay to make and some are not. Like to get good experience and like to be a like wield FEA responsibly, you have to just build up some intuition that only comes with time on what the usefulness and limitations of it is. Like it is not a crystal ball, and it should always be like double checked either with experimental data, or if you can make some hand calculations, like approximations, even if they're off there, you should see if you're getting within the same order of magnitude of what your value is. And if you're getting really uncomfortably close to what your failure criteria is, maybe you should consider buffing up your geometry, or just being on the safe side, or choosing a more conservative failure theory. Where certain uncertainty comes in analysis, Colin, I don't know if you want to speak to this slide a little bit more, but like some certain things you can actually represent a little more than better. So like your solid model, you can feel pretty confident on, but like, I don't know if you want
So this is stolen from like a solid theory book, which then stole it from a good textbook that like Chris Lee recommends, which is called Building Better Products with FEA. But they like do like actual statistical analysis of like where uncertainty comes from in the analysis process, and then just graphically represented it here. So this is just kind of just to give you some signal when it comes to like where does like error come from in a tungsten analysis, and where should I look to of like where I want to put my energy towards, of like what's going to give me the most bang for my buck of like finding error. And if you really want to look in depth, I can provide like the digital copy of the textbook, but this just gives you at least something to go off of.
Cool. Yay, Carlos is going to shut up now. We're going to do stuff. If you go to your Canvas day assignment for today, we are going to do just a really simple cantilever beam analysis. And so if you've never run FEA before, it's been a minute. It's a very kind of like hands-on step by step. We'll show you what buttons to click and like what the different settings can do. We're going to run a really simple, just kind of like hand calc. We're going to run FEA, and then you guys are going to see like what the result options and outputs are and how that relates to the failure theories we were talking about earlier. Yay! Was this useful? Like, cool. I know it was a kind of very heavy, just stare and watch while Carlos talks, but The assignment that's on Canvas, actually, I'll just pull it up. It's like FEA beam in class. It was very graciously inspired by Chris Lee's class. If y'all that are seniors, unfortunately, you probably won't be able to take FEA, unfortunately, unless he offers it next semester, but I don't think he will. Highly recommend you guys take it. How do let's stop share. Oh wait, no, not, I actually don't want to stop share. I want to share this screen. Here we go. There's a lot of stuff that like, if
They still.
they can't on Zoom. I can't. Oh wait, they can't hear. Haha. Technology is great. Okay, and then here we are. It's this is borrowed from Chris Lee's class. You'll notice that there's some things that just like don't have very like explicit directions. So like do hand calculations for deflection at the tip and like apply a small downward force. It doesn't explicitly give you directions. I recommend y'all play around with the values and see if it gives you like reasonable assumptions. And then there's a few things where if it doesn't feel useful, or if we haven't talked about it, you don't actually need to write down, but you should maybe consider looking up. And the most useful thing is that if you come down here, there is, it gives you access to SolidWorks like help figure, and it gives like directions and like explanations for each one of the FEA outputs is. But fun stuff.
With a small force, like the force that you put in is giving you, like, do you want to run like a large displacement solver? It probably means no small. And then you're actually not assuming small displacements anymore. Big displacement.
Anything about someone who hasn't taken an FEA, like good for you.
This, I, as an airplane person, I'm not sure. Yeah, I was gonna say, isn't the mechanic, like, is the Mechtas project just like keep it blind?
Yeah.
Yeah, it is.
How's that go? I'm not in Mechtas. Yeah.
Like,
It's just like funny.
like we
This is
related
like-
to that, like,
Like,
oh, you
road.
related it.
Oh, no, it's like, I mean, it's totally out of context.
It's gonna be like.
That's hilarious, actually.
I think it's just too much. It's not. I don't know.
What was Dave doing?
We're just talking about like the infinite stuff, and I think it was very reasonable. But when you put it side by side,
That's actually hilarious.
I think a lot of times I'm there.
I think he wants to say groundwork and then
I just feel like there's a perfect meaning.
I'm just
like.
Did you write mech-analysis? I had it, and that was so funny.
Their research into everything.
Really, every post, waiting for every class.
This is
Yes, we're not a research institution. We're not a research institution.
Didn't Whitney have like actual like NSF people come by?
Yeah, you could ask anyone in ABC about it. They have to present to like NSF every week or something.
Apparently they were very hyped for this presentation too.
NSF?
Yeah, they're like, when you're doing this, and I was just like, they kind of put it together in like a less than a week's time.
Wait a minute, I should be getting.
You're paying.
Yeah. That's funny though. Struggles to live through vaccines. It's like, we all know.
What literally, he did show your.
Yeah.
It's a weird.
Where
You feel about that point? Or I guess that was more SED. Is it line thing?
yeah, you're in the yeah, Colin, decentralize yourself, please.
I don't know if they go the phone. Yeah, they really offended us. Funky detail.
I think you did it primarily just because of cost, being able to get some for the class.
Yeah, he said he was gonna buy that on Alibaba. So.
I think you did.
Pretty sure he did.
I forget what.
Hey, they'll be here by December.
Right, in 1 week, build your plane.
Like, where the big boys. I don't know.
Someone at the start of the semester for 2 North was saying like on Alibaba you can get like custom logo like red solo cups for like 2 cents per cup. and I was like, okay, but they're gonna get here by January. Like,
I need a second semester.
yeah.
Like for ABC. I think I figured out what part of the plane.
None of it.
I don't know. I don't think anyone knows that those stuff like. Like, you know, right.